Okay, brother. So we have two kinds of things in the nonlinear programming problems with no constraints. I am talking about the unconstrained problems. Okay, this is for the unconstrained problems. The problems are nonlinear programming problems which have no constraints, zero constraints. Okay, we have two kind of things in the unconstrained: the quadratic forms and the non-quadratic form. The quadratic form are those which have a degree of 2 in each of the term. Okay, for example, we have f of x is equal to x1 square plus 2x1 x2 plus 2x2 square. So in this one we have a degree of 2 over here. This is a combined degree of 2 over here, 1 degree for x1 and 1 for x2, and here we also have a degree 2. So this is the quadratic form. Okay, and we don't have degree 2 in each term in the non quadratic form. Okay, in this we can say that f of x is equal to, for example, x1 square plus 2x1 x2 plus 4x2. Now here we have degree 2, here we also have degree 2, but here we have only degree 1. So this term is lagging actually here, and it is not having a degree 2 over here. So this is the non quadratic form. Okay. Now when we have the quadratic form actually, then we use the symmetric matrix method to find the local maxima or minima, and when we have the non quadratic form in the unconstrained problem, we have used the Hessian matrix h of x to find the local minima or maxima. Okay. So we can write the function, quadratic function, in this form: f of x is equal to x transpose a into x, where x is equal to x1 x2 x2 x3 up to xn. These are the decision variables. Okay, the number of decision variables. For example, in this one we have two decision variable x1 and x2. Okay, so here the x will be equal to x1 and x2 only. Okay, and there are two decision variables, so the A matrix, it will be 2 cross 2. It means that it will have 4 elements, which is a11, a12, a21 and a22. Okay, and a11 is equal to C11 and a12 is equal to C12 divided by 2, and a12 is equal to a21. These are the certain properties that we know about the quadratic forms. Okay, now you must be wondering what is C11 actually. Okay, so let's get an example like f of x, the above example, x1 square plus 2x1 x2 plus 2x2 square. Okay, now we know that f of x in the quadratic form is equal to C11 x1 square plus C22 x2 square plus C33 x3 square plus and so on up to Cnn xn square plus C12 x1 x2 plus C13 x1 x3 and so on. Okay, this is the general form of it. Now the C11 actually here is the coefficient for x1, the first variable. Okay, the C22 is the coefficient for the second variable, and C12 is the coefficient for when we have two variables in a single term, x1 and x2 over here. So the coefficient is C12. Here we have x1 and x3, so the coefficient is C13. Okay, now if we see this function over here, okay, the C11 over here is equal to, this is, we can write it as 1x1 square. So the coefficient of x1 square is 1, so C11 is equal to 1. The coefficient of x2 square is 2, so C22 is equal to 2, and C12 is equal to C21 okay, and it is equal to the coefficient for x1 x2 and it is also 2. So a11 is equal to c11 is equal to 1, a1 a22 is equal to c22 is equal to 2, and a12 is equal to a21 is equal to c12 divided by 2. What is c12? It is equal to 2. So 2 divided by 2 is equal to 1. So we can actually we can write this function as x is equal to x1 x2 because we have only two variables over here, okay, and the matrix is 2 by 2 matrix and it is a11 a12 a21 and a22. So what is the value of a11? A11 is the value, it is equal to 1. So a is equal to 1, a12 is equal to a21 is equal to 1. So 1 1 1 and here it is 2. So this is the symmetry matrix that can be used to solve this function actually, okay. Now I will go to the non-quadratic forms and we will find the Hessian matrix, okay. Now when we have like the unconstrained non-quadratic form of functions, then we use the Hessian matrix which can be denoted as h of x, okay. Now this h of x, it is also n cross n, but the numbers over here, these are not like the symmetric matrix, okay. The numbers over here are the first number over here, it will be the second order derivative of this function with respect to x1, okay. The first order is also with respect to x1 and the second one order is also the according to x1, and then the first order derivative with respect to x2 and the second order derivative with respect to x1, and then the first order derivative with respect to x3 and the first order derivative second order derivative with respect to x1 and so on, okay. And then the first order derivative with respect to x1 and second order derivative with respect to x2, and here it will be the first order derivative, okay, it will be with respect to x2 and the second order derivative will also be with respect to x2. So we can write this as like this dx2 square. It means that both the derivatives, the first order and the second order, are according to the x2, okay, and so on, okay. And here, and we can write, we can the in the vertical we go from x1 to x2 and x3 second order derivative, okay, and in the row form we go from x1 x2 x3 and so on, and in the column form we also go from x1 x2 and x3 and so on for the second order derivative, okay. So this is the h of x, this is the Hessian matrix, okay. I will do an example on it and you will understand, you will come to know like how this is actually done. For example, we have a function is 2x1 plus 3x2 minus x1 square minus x2 square. Now we see that here we have degree 1, here also degree 1, here 2 and here is also 2. So it is a non-quadratic form. So we know that when we have like non-quadratic form, we need to find the h of x, okay. Now we have the variables over here are, here we have x1 and x2, x1 and x2. So only two variables are in consideration. So the h of x actually it will be in 2 cross 2 form. Okay. Now we know that the first this one the first element it will be that the first derivative it will also be with respect to x1 and the second order derivative will also be with respect to x1. The second one will be that the first order derivative it is done with respect to x2, but the second order derivative with respect to x1. Here the first order derivative it will be done with respect to x1, but the second order derivative it will be done with respect to x2, and the third one the fourth element it will be that both the order derivatives are done with respect to x2. Okay. Now we also know this there is a rule that d square f into dx2 dx1 is equal to d square f divided by dx1 dx2. It means that if we it means that if the first order derivative is made according to x1 and the second order derivative is made according to x2, then it is equal to the first order derivative made according to x2 and the second order derivative done according to x1. Okay. Okay. Now we will solve this non-quadratic form equation or function, and we will find the Hessian matrix for it. Now for this actually first we need to find the first order derivatives. Okay, first order derivatives, and we will derive this function with respect to x1 as well as with respect to x2. So let's suppose first we do it with respect to x1, then it is equal to d by dx1 actually of this function 2 plus 2x1 plus 3x2 minus x1 square minus x2 square. Okay. Now it is a number actually, so the derivative it will be 0. Okay. And for the 2x1 it will be 2 into 1. Okay. How it is found, we can do it as like d by dx 1 of 2x1 is equal to 2 into d by dx1 of x1. So it will become 1. So it is 2 into 1 is equal to 2 actually. Okay. Now plus this is x2, so it will become 0. It is x1 square, so the it will become like 2 into x1, and d by dx of x1 is 1. Okay, minus it is x2, so it will also become 0. So d by dx1 of f it is equal to 2 plus 2x1. Okay, so this is the first order derivative with respect to x1. Now the first order derivative with respect to x2 for this function it will be, this is the partial derivative. Okay, x2 2 plus 2x1 plus 3x2 minus x1 square minus x2 square. Okay, this will become 0. Okay, this is x1, so it will also become 0. This is x2, so it will become 3 into 1 minus this will also become 0 because it is x1 minus 2 x2, so it will become 3 minus 2 x2, and it is the first order derivative of this function with respect to x2. Okay, now we need to find the second order derivatives for each of the element to be found. Okay, now we will find the second order derivative of this function. Okay, now the first order derivative of this function is with respect to x1 is 2 plus 2x1, and the first order derivative with respect to x2 is 3 minus 2x2. Yes. Okay, so okay, now the second order derivatives. Okay. Now for the second order derivative we will do this with respect to x1 and x2 as well, and then with respect to x1 and x2 as well. So d by dx1 of the d by dx1 of f, it will be equal to 2 plus 2x1. So it will give us d square f with dx1 square, and it will give us the derivative of 2 will be 0, and the 2x1 it will be 2 into 1, it will become 2. Okay. Now with respect to WRT means with respect to, okay, with respect to x2 second order derivative. Okay. Now we can say that d by dx2 of d by dx1 of f. So this is already found. So d by dx2 of this is equal to 2 plus 2x1. Okay. Now with respect to x2, this 2 will yield 0, and with respect to x2, 2x1 will also yield 0. So it will become 0. So we know we can say that the d square f with respect to x2 and x1, it means that the first order derivative was with respect to x1, and this one means that the second order derivative is with respect to x2, and it will be equal to 0. And we know that it is also equal to the, when we take the first order derivative as with respect to x2 and the second order derivative with respect to x1. Okay. Now taking the second one, this is when we take the first order derivative with respect to x2, and we got 3 minus 2x2. Now taking second order derivative with respect to x1 and x2 respectively. Okay. So first regarding x1, we can know that this is also, so we can also write it as equal to 0, but if we take it, for example, we don't apply this rule, we want to make it happen, then it is equal to, this will become 0 minus 2 into d by dx, the derivative of x2 with respect to x1 will yield 0. So it will become 0. So this rule is verified. Okay. Now with respect to x2, it is equal to d square f with dx2 square, and it is equal to d by dx square of 3 minus 2x2. So 3 will yield 0 minus 2, and d by dx of d by dx2 of x2, it will yield 1. So it will become 0 minus 2 into 1, it is equal to minus 2. So the Hessian matrix is equal to, the first one is d square f divided by dx1 square, and here we have it is equal to 2. So we will write 2 over here. The second one is that the first derivative is taken with respect to x2, but the second order derivative is taken with respect to x1, and it yields 0. So it is 0. And the third one is that the first order derivative with respect to x2 and the second order derivative is with respect to x1, and it is also 0. So it is 0. And the fourth one is the d square f divided by dx2 square. Both order derivatives are taken with respect to x2, and it yields minus 2. So this is the Hessian matrix for the non-quadratic problem. Okay. Okay. One other rule is that Hessian matrix is equal to 2 into the symmetric matrix, or symmetric matrix is equal to Hessian matrix divided by 2. So if one matrix is given, we can also find it from the other one. Okay. So this is the general rule. Okay. We can also verify it, but it will take some time. For example, I do it for the same problem. we can easily find it. Okay, now this is the main course. Actually, I just want to lecture. This lecture was all about this thing, to find the local maxima and minima for a quadratic or non-quadratic form. Okay, so it is done in basically 3 steps. Okay, the first step is to find the stationary points. You can say that x is steric, okay, such that the partial differential of this function with respect to x1 is equal to the partial differential of this function with respect to x2 and is equal to the partial differential with respect to xn, and it is equal to 0. Okay, then we check the matrix corresponding to quadratic or non-quadratic form for its definiteness. So check the definiteness of the matrix. Okay, we will come to this. Okay, but let me do this 3 steps. Okay, and then the x steric that we found, it is either the local minima if the matrix is positive definite, and x steric is equal to local maxima actually if the matrix is negative definite. Okay, and the third one is that x steric is equal to saddle point if the matrix is indefinite. Okay, so to check the definiteness we have some rules to follow. Okay, and I will explain all the rules over here. The definiteness of the matrix, we have like 5 different forms of it. Okay, we have the positive definite. Okay, then we have positive semi-definite, negative definite, and negative semi-definite, and the last one is indefinite. Okay, there are some rules that we need to follow, or we see the conditions and say that whether it is definite or in fall in these categories, any of these categories. Okay, for the positive definite, actually positive definite, we say that if f of x is greater than 0 for all x not equal to 0. Okay, and this is the bigger x, and x is equal to x1, x2, x3. It means that x1, x2, x3 can carry the value of 1, 2, 3 and up to infinity, but not equal to 0 or below that. Okay, and we get the function value as greater than 0, then it is a positive definite. For example, we have a function over here that is x1 square plus 5x2 square plus 7x3 square. Now we have 3 variables over here. Okay, if we put x1 is equal to 1, x2 is equal to 1 and x3 is equal to 1, we see that f of x we get greater than 0. Okay, similarly if we put x1 is equal to 5 randomly, x2 is equal to 3, and x3 is equal to 9 for example, then we also get f of x greater than 0. So it means that this function is positive. The matrix that we get will be the positive definite. Okay, now for the positive semi-definite, actually the f of x, actually it is greater than or equal to 0 for all x not equal to 0, this capital X, but there exists at least one non-zero element, or we can say variable, for which f of x is equal to 0. For example, we have a function, let's say that a function is x1 minus x2 whole square plus 2x3 whole square. Okay, now we say that if we take x3 is equal to 0 and x1 is equal to 1, x2 is equal to 1, then f of x is equal to 0. Okay, and besides these, for all x is equal to x1, x2, x3 and is equal to 1, 2, 3 and so on, it will be greater than 0. So only in one condition it is equal to 0, so it is semi-definite. Okay, now I will explain the other three. Okay, one is the negative definite. In the negative definite, actually f of x will be less than 0 for all x not equal to 0. Okay, and similarly for the negative semi-definite, f of x will be less than or equal to 0. Okay, for all x not equal to 0, and there exists one for which f of x will be equal to 0 or like that. Okay, and there is indefinite one. Indefinite is when all the above other rules do not follow. When we do not have any like this, then it is an indefinite. Okay, so for all to find the whether a matrix is positive definite or negative definite or indefinite, we have a matrix minor test. Okay, matrix minor test. Okay, in this test, actually what we do is we say that the d1 is equal to a11 for the positive definite. The rule is that d1 is equal to a11, that is the first element of the matrix, it is must be greater than 0, and d2, which is the square determinant, it also should be greater than 0, and d3, which is the 3 by 3 determinant, it also should be greater than or equal to 0. Okay, and for the positive semi-definite, okay, we can say that for the positive semi-definite, actually the d1 is greater than 0 and di are greater than or equal to 0. It means that the first one element, the a11, it should be greater than 0, and the all other di determinants, okay, it must be greater than or equal to 0. Okay, Here we only say that greater than 0, and here we say that greater than or equal to 0. So if the second determinant, that the square matrix determinant, is equal to 0, then it is the positive semi-definite. Okay, third is the negative definite. If for this the d1 is less than 0 and d2 is greater than 0 and d3 is also less than 0, so it comes into alternate one. The first one is negative, the second one is positive, the third is also negative, the fourth one is also positive, so it is negative definite. The negative semi-definite is when the first one is negative, the second one is either positive or equal to 0, the third one is less than 0 or 0. So it has it can be like equal to 0, and d4 is also greater than 0 or equal to 0, so it is a negative semi-definite. And indefinite, when all of the above, any of the above does not hold, then it is the indefinite one. Okay, now I will solve some questions and you will understand that how we classify it as positive definite or negative definite or indefinite. Okay, we have an example which says that find stationary point and classify it as maxima or minima. It means that find the maxima or minima of the function. Okay, and the function that is given is 2 plus 2x1 plus 3x2 minus x1 square minus x2 square. Now the first thing that we look over here is that whether it is quadratic or non-quadratic, which matrix that we need to find out. Okay, here we have degree of 1, here degree of 1, here degree of 2, and here also degree of 2, so it is the non-quadratic one. Now we have non-quadratic one, then we find the h of x. Okay, now here the h, we know that we have x1, x2, we have only two variables over here, so we have like 2 cross 2 matrix. Okay, and the first one is when we make both the partial derivatives with respect to x1. Okay, the second one is when we make the first derivative with respect to first order derivative with respect to x2 and the second order derivative with respect to x1, and the third element, that is the first column element, is when we make the first order derivative with respect to x1 but the second order derivative with respect to x2, and the fourth element is when we make both order derivatives with respect to x2. So for that we need to find the first order derivatives first. So the first order derivative, okay, so with respect to x1 it will be equal to this will become 0. This is regarding with respect to x1, so it will become 2 into 1 plus it will become 0 minus 2x1 minus 0, it will become 2 minus 2x1. Okay, and this is the first order derivative. Now getting the first order derivative with respect to x2, here it will become 0 plus it is x1 and it is with respect to x2, so it will also become 0. This is x2 with respect to x2, it will become 1 and it will become 3 into 1. Okay, minus this is x2 and we want to differentiate x1 with respect to x2, so it will become 0 minus it is x2, it is also x2, so it will become, the power will come forward, and d by dx of x2 it will become 1, so we will get 3 minus 2x2 as the first order derivative with respect to x2 for this function. Okay, now we will find the second order derivatives and we find the Hessian matrix. Okay, so we have the first order derivatives. Now getting to second order derivatives. Now second order derivative of this first order derivative with respect to x1 again with x1, so it will become, so we get over here is 0 minus 2, so minus 2. Now for this one, doing it with respect to x2, so d by dx2 of 2 minus 2x1 is equal to, so it will become 0 minus, and 2 into 0 it will become 0, so it will become 0, okay, with respect to x1 and x2. So this is for the first one. Now for the second one, we will do it with respect to x1, so it will be equal to d square f with respect to, okay. Now doing this one with respect to x1, so you will get, you will get 0 over here. Also, even if you don't find it, it is equal to this one. And now doing it with respect to x2, so here we will get 0 minus 2 into 1 is equal to minus 2, and it can be written as d square f by dx2 square, and it is equal to minus 2. Now we know that the Hessian matrix is 2 by 2 matrix, and the first one is the this one, the d square f by dx1 square, which is equal to minus 2. Now the second one is equal to 0, the third is also 0, because d square f, the first order derivative with x1 and second order derivative with respect to x2, it is equal to 0, and it is equal to the first order derivative with respect to x2 and the second order derivative with respect to x1, okay, which is this one, okay. Now both the order derivative with respect to x2 we got minus 2, so we will get minus 2 over here. So this is the Hessian matrix for the said problem, or with the for the respective problem. To find the stationary points, actually for stationary point, we have the differential of the function with respect to x1 is equal to differential of x2, the function with respect to x2, and we equate it to 0. So the differential of the function with respect to x1 is this one, okay, 2 minus 2x1, the first order, and the first order differential of the function with respect to x2, we get the value 3 minus 2x2, okay. Now we equate both of them equal to 0, so implies that 2 minus 2x1 is equal to 0 and 3 minus 2x2 is equal to 0. So we solve it for x1 and x2 respectively, so we get 2x2 is equal to 2 and x2 is equal to 1, and here x1 is equal to 1, 2x1 is equal to, and here it is for x2, so we get 3 is equal to 2x2. This 2x2 will come over here, so it will become positive, so we can say that 2x2 is equal to 3 and x2 is equal to 3 by 2 or 1.5. So x1 is equal to 1 and x2 is equal to 1.5. So the stationary points x steric is actually equal to 1 and 1.5. Now we want to know that if this stationary point is local maxima or minima. To find whether it is local maxima or minima, we need to do the matrix minor test, okay, minor test, and it is done for the symmetric or the Hessian matrix. Now the Hessian matrix HIX is equal to minus 2, 0, 0 and minus 2. Now we see that the d1 is equal to a11, and a11 is over here is equal to minus 2, which is less than 0, okay, and d2 is the determinant of the 2 cross 2 matrix, which is equal to minus 2, 0, 0 and minus 2, and we get is minus 2 into minus 2 is equal to 4, minus 0 into 0 is 0, so we got 4. So d2 is equal to 4, which is greater than 0, okay. So now we see that there is a pattern, d1 is less than 0 and d2 is greater than 0, so it follows an alternate pattern. Now we know that when we have an alternate pattern, then it is negative definite, okay, and when the matrix is negative definite, it means that the stationary points that we found, this is the local maxima, and the z value for this, the function value or z value for this is 2 plus 2 into x1 is 1 plus 3 into x2 is equal to 1.5 minus 1 square minus 1.5 square. So we get over here is 2 plus 2 plus 4.5 minus 1 minus this is 9 by 4, something like that, okay. So when we add and subtract this, we get 3 actually 21 by 4. This is the last answer that we get. We got 4, 4.5, 8.5 minus 1, so it become 7.5. 7.5 is 15 by 2, so 7.5 it can be written as 15 by 2. So 15 by 2 minus 9 by 4, we get 21 by 4 from that. So this is the maximum value that we can achieve from this, and it is the local maximum value. We have another example for the local maxima or minima. In this it says that identify the relative maxima and minima for the function, and the function is equal to 25x1 square minus 8x1 x2 plus x2 square. So we see that here it is degree 2, here is also degree 2, and it is degree 2, so it is quadratic form, okay. So when we have quadratic form, then we find the A matrix. So now here x1 and x2, here the x is equal to x1 and x2, only two variables involved, so the A matrix is equal to a11, a12, a21 and a22, which is 2 cross 2, okay. And we know that a11 is equal to c11. C11 is the coefficient for x1 square, so it is 25 over here, okay. Now a12 is equal to a21 is equal to c12 divided by 2. Now c12 is the coefficient for x1 x2, which is minus 8, so minus 8 divided by 2 is equal to minus 4, okay. And a22 is the coefficient for x2 square, so it is 1 over here, so it is 1. So we can write the matrix straight away. A11 is equal to 25, a12 is equal to a21 is equal to minus 4, so we can write minus 4 and minus 4 over here, and a22 is equal to 1. So this is the A matrix, symmetric matrix, okay. Now we found the symmetric matrix, okay. After that we need to find the partial differential with respect to x1 and x2 for the function. For partial differential, we say that the d by dx1 for the function is 25x1 square minus 8x1 x2 plus x2 square. So it will give us 25 sorry 25 into, it will give us 2x1 into 1 minus 8 into, here we have x1 and x2 as well, so x1 will become 1 actually, so it will give us 8x2 plus 2x2 square, it will become 0, as we have, it is only purely x2, so it will become 0. So we will get 50x1 minus 8x2, and it is the partial differential with respect to x1. Now the partial differential with respect to x2 for this function is equal to 25x1 square minus 8x1 x2 plus x2 square. Okay, it will get 0 because it is x1 only over here, so it will become 0 minus 8x1 plus 2x2 into 1. So we will get 2x2 minus 8x1, which is the partial differential with respect to x2 for this function. Now we need to equate both these two with equal to 0. Implies that d by dx1 of function is equal to 50x1 minus 8x2 equal to 0. So which implies that 50x1 minus 8x2 is equal to 0, and for the other one we get as 2x2 minus 8x1 equal to 0. Now we have two equations over here. The first one is this one, the second one is this one. So we need to find a way, to get the value for x1 or x2. Okay, we can write the second equation as minus 8x1 plus 2x2 is equal to 0. Okay, now here for the x2, here we have 2, and here we have, for the x2 we have 8. So we need to equate both these. So multiplying the 2, multiply 2 with 4, we get 8 into 4 is minus 32, so we get minus 32x1 plus 8x2 is equal to 0. Now we subtract 2 from 1. Sorry, not subtract, but because here we have negative, so we just need to add it. Okay, now add 2 to 1, we get okay. So we have now 50x1 minus 8x2 equal to 0, and have 32x1 plus 8x2 is equal to 0. Okay, when we add both these, we get 18x1 is equal to 0, which means that x1 is equal to 0. Now for x1 is equal to 0, we find the x2 and we put it in 1 using substitution. Okay, we substituted. So 50 into 0 minus 8 into x2 is equal to 0, implies that x2 is also equal to 0. So the point, stationary point, is 0 0. x1 is equal to 0, x2 is equal to 0. Now we need to find whether this point is local maximum or minimum for the function. Okay, for that we do the matrix minor test. Okay, now the d minor, the d first is equal to a11 is equal to 25, and 25 is greater than 0, so the first determinant is greater than 0. Now the second one is d2 is the determinant for the square matrix, and it gives us 25 minus 4 into, and this is 1, so it will give us 25 minus 4 into 4 is 16, so it will give us 9, and 9 is also greater than 0. So we know that d1 is greater than 0 and d2 is also greater than 0. So it is positive definite. It is, the matrix is positive definite, and we know that when the matrix is positive definite, then the point, the x steric is equal to 0 0. This is the local minima, and that is how it is solved. Thank you.